Welcome to our ESA special program about Euclid. I'm Sandra Benitez, and we are here today at the European Space Agency at its Space Astronomy Center in the outskirts of Madrid. Today, we will discover the latest results from our fabulous Euclid Space Telescope that is designed to understand better the nature of the universe, especially dark matter and dark energy. Euclid is an European mission built and operated by ESA with contributions from NASA, and it was launched 1 year ago in July 2023. The Euclid Consortium, consisting of more than 2,000 scientists from 300 institutions in 15 European countries, the US, Canada, and Japan, provided the scientific instruments and scientific data analysis. We are very excited to be here with all of you. But before we start, a word of introduction by ESA's Director General, Joseph Asbacher.
Welcome everyone to this exciting program where we will show stunning, never-before-seen images from space that reveal more about the structure of our universe. Euclid, launched in July last year, is ESA's latest mission dedicated to mapping the cosmos by observing billions of galaxies across space and time. It will reveal more about the most mysterious stuff around us, dark matter and dark energy. These make up 95% of space, but no one fully understands what they are. Euclid shows star-forming regions in unprecedented detail, uncovering 300,000 new objects in one shot, including free-floating planets that are 4 times the mass of Jupiter. During its mission, Euclid will help us to better understand our universe, what it is made of, and how it has expanded and evolved over cosmic history. Euclid demonstrates the unique expertise of ESA. These images are the result of many years of hard work from scientists and engineers throughout Europe and from members of the Euclid Scientific Consortium around the world. Let's watch now as we gain a tantalizing glimpse into the nature of the universe and the very foundations of our cosmos.
And here with us today, we have a very special guest, Professor Carol Mundell, ESA Science Director and Head of the European Space Astronomy Center in Madrid. Thank you, Professor Mundell, for being here with us.
It's a real pleasure to join you, Sandra, on this special day.
Professor Mundell, what can you tell us about this incredible mission?
So the Euclid mission is our dark detective, and this is an incredible mission that we launched last year. And the big question that it wants to answer is what's the 95% of the universe that we don't understand? We want to understand the physics of dark matter, the nature of dark energy, and all of the stuff in the universe that actually is not the normal matter that makes stars and galaxies and people. And so it's a really exciting mission. It's phenomenal in the technology because we have an incredible reach, very big field of view, very sensitive detectors, and exquisite crystal clear vision. So pulling all of those together with its autonomous survey capability and the big international collaboration that we've pulled together to do the science makes it an iconic and unique world-leading cosmology mission.
Thank you, Professor Mundell. And what is the connection between Euclid up to space, 1.5 million kilometers away, and ESA here in Spain?
So what's really special about ESA, as you said, it's the European Space Astronomy Center. So this really is the home of science for ESA and for our 22 member states. ESAC represents ESA in Spain, and we have a very strong and close collaboration with the Kingdom of Spain, who kindly host us here on this special site. And although we call this the home of science, it's where we have our science operations centers and where we will actually pull all of the final data for Euclid together in our wonderful archives. We also have this digital library of the universe. So all of our science missions, be they planetary, be they solar, be they galactic, or be they cosmological, all of the data end up here, worked on by our experts at ESA, supporting our member states and their scientists. And not only do we have the home of science here, but we have a very strong educational program, inspiring the next generation through these big iconic cosmic questions at the forefront of technology. And last but not least, least, not only do we have science on the site, but it's my privilege as head of establishment to host directorates from across the agency. So, for example, our colleagues from navigation, who lead on the Galileo satellites, our colleagues from Earth observation, who look down on the Earth and help us to understand the science of our own home planet, how to protect it and keep it safe, but also to put that planet into the context of the wider understanding of planets and the rest of the cosmos that we study in our science program.
Thank you, Professor Mundell. We are now going to unveil the new 5 pictures taken by the Euclid Space Telescope together with the scientists using the Euclid data. Professor Mundell, what can you tell us about the unveil of today?
So today is a very special day, Sandra. So these are the first time the world will have seen these incredible images. These images were taken in our early release test campaign, and what we're actually doing today is bringing the scientists together to explain the fundamental research that these images have enabled. And going through them, you'll be able to see the power of the Euclid mission, not only to answer that fundamental cosmology question about dark energy and dark matter, but also to understand what else makes up the universe, from galaxies to stars, right down to Jovian-sized planets. So it's a very powerful mission, and I think you'll get a flavour of that today with the first sight the world has ever had of these new images.
And you wanted to comment on a particular image today that is very special.
I did. I wanted just to show the very first image that actually our Director General Joseph Aschbacher will have released in a sneak peek to ministers in Brussels today. And it's our great privilege to be able to show this incredible galaxy cluster. And the reason that this is special is because the scientists are using what they can see in the light to try to trace what we cannot see in the dark. So we will hear more from our scientists later on explaining how exactly they do this. But this actually gives me goosebumps when I think about the power of Euclid to really unveil the hidden cosmos.
Thank you, Professor Mundell, for being here with us today.
Thank you.
And we are now going to unveil the rest of the images. We are now ready to discover the first Euclid image, Messier 78. And for that, we have here with us today Dr. Marusha Jerial and Jerry Chan from the Institute of Astrophysics of the Canary Islands. Welcome, Marusha and Jerry.
Thank you.
Let's first discover the image, and we will come back to you in 1 second. Marusha, what can we see in this picture?
Look at this stunning image of vibrant stellar nursery. This is Messier 78. It's enveloped in hydrogen gas that's being illuminated by very hot and massive stars that recently formed in the core of this cluster. But we also see dark filaments of interstellar dust. This region is located at about 1,300 light years away, which is pretty close in astronomical sense. It's actually in the solar neighborhood.
And how is this view unique?
This image is unprecedented because this is the first such image of such width, depth, and sharpness. And such large field of view actually enables us for the first time to study objects of very low mass to such details and in uniform manner. And this is pretty unique because this is the first time we can do this, and it hasn't been ever possible before.
Jerry, why is Euclid the only space telescope capable of capturing this kind of view?
Euclid is the only wide-field space survey telescope that's covering the near-infrared wavelength. And the near-infrared light can penetrate dense dust and gases. Euclid near-infrared camera is so sensitive that has already unveiled the hidden regions of star formation for the first time. And with one shot, Euclid has uncovered 500,000 of objects, including galaxies and stars.
Marusha, what can we learn scientifically from this image?
In images like this from Euclid, we can study the number of newly formed stars, but also the number of objects that are less massive than stars. They're called brown dwarfs. And we're interested to see how they form and how they evolve through time. But also, some of them are born as twins, which is especially interesting because they can tell us much more, they can give us much more information about their evolution and their properties. And what's the most exciting parts are objects that are, some of them are even a few Jupiter masses. They're called free-floating planets or rogue planets. And this is the most interesting part of this image.
So Jerry, can you tell us a bit about the connection between dark matter and what can we learn from it?
Dark matter, as we all know, is so mysterious and is invisible, but so far. Brown dwarfs and planetary mass objects are actually candidates for this missing mass. However, the individual object has so little mass that we have to find significant number of them to support this idea. So far, even in the solar vicinity, we still believe that we only found the tip of the iceberg. We have to find the slightest object as much as possible and as far away as possible to characterize this population. As Marusa said, Euclid will help us to make one step further.
Let's go on with our second picture from the Euclid spacecraft, NGC 6744. To comment on it, we have with us Dr. Francesca Annibali from INAF Astrophysics and Space Observatory in Bologna. Welcome, Francesca.
Hello.
Let's enjoy the view and we will come back to you in a few seconds. Francesca, what can we observe in this picture?
So here Euclid imaged NGC 6744, which is one of the largest spiral galaxies beyond our local patch of space. And this is an example of the typical galaxy that's forming stars in the nearby universe. And what is amazing about Euclid is not only the possibility to image in just one shot the entire galaxy with this beautiful spiral structure, but also to reveal the finest details on small scales.
What do you mean by a small scale? What kind of detail are we talking about?
So you can see here, we can even count individual stars and reveal the distribution of dust. We see all these feather-like dust lanes coming out from the spiral arms like spurs. So we really have a detailed distribution of dust and stars here in this galaxy.
And we can also see newly born stars with unprecedented detail, right?
Yes, and while it is quite common to have a detailed view of small portions of star-forming regions, it is quite rare to have such a detailed view for a whole galaxy, and so detailed view for all the star-forming regions that are around it. And consider that forming stars is the main way through which galaxies grow and evolve. So this kind of studies can really help us understand why the universe looks the way it is today.
So what can we learn from the scientific point of view with these images?
So from this kind of data set, we can understand the physics of spiral structure and the connection to star formation, which is something that is not yet fully understood despite several studies in the last decades. And furthermore, we can also hunt for new dwarf galaxies around this giant spiral. And indeed, we discovered a new one just right there. And this discovery was quite unexpected because these galaxies had been studied a lot in the past, but this showed really the high potential and power of Euclid in such kind of studies. And we really, in the future, we will be able to study thousands of nearby galaxies in such high detail, and we really expect new exciting discoveries to be done.
Thank you so much, Francesca, for this insight on the spiral galaxy NGC 6744.
Thank you so much.
We are now going to discover picture number 3, Dorado Galaxy Group, with Dr. Karina Vogel and Dr. Taimur Seifolahi from Strasbourg Observatory. Welcome to our program.
Hello.
Let's enjoy the view and we will join you in a few seconds. Karina, can you describe this picture for us, please?
Yes, of course. So what we here see is really a stunning view of what we call the Dorado galaxy group. A galaxy group is typically a lot of galaxies, but it's a little smaller than a large galaxy cluster. And here we can see its two main members in the very center. These are two big old elliptical galaxies. And what we can see is that they're currently interacting. And we see that because they have shells and tidal feature that kind of go all around them that basically showcase this type of interaction, that it's ongoing. So we see galaxy evolution as it's happening, and as a signpost of these processes while it's going on. And in galaxy evolution, it's essentially like this, how we understand how they evolve and merge together to form one larger galaxy. And this showcases it beautifully, this type of galaxy evolution.
But Taimur, we're also looking at additional objects in this amazing image, right?
Right, Sandra. If you have a closer look, for example, to the central galaxy in the Dorado group, you see all these little points look like stars. Well, most of them are background, high redshift, very distant galaxies. But some of them also, while they look like a star, they're actually accumulation of tens or hundreds of thousands of stars together, objects that we call global clusters. These are part of the galaxy system here, the part of the Dorado group and around this galaxy. The interesting thing about this object is that they are very old. They formed with the galaxy early on, about 10 billion years ago or even more, and so they experience the same as the galaxy experienced throughout its life. So they can tell us even more about what galaxy has been through over these billions of years, and we can learn more about the galaxy evolution.
This is so interesting. And Karina, how did Euclid get this sharp picture of the universe?
So the really revolutionary thing about Euclid is that it can look at such a big field of view, such a big area in one go. So it can take a large photo. And that enables us to really study everything, not just single little patches of the centers of galaxies like we did previously, like with the Hubble Space Telescope. And that combined with its spatial resolution, essentially, we see all the fine detail. We can study those global clusters. We can study those tidal features. And in the end, the goal is, and what Euclid will provide, is to have this global view of these objects and not just little postage stamp studies. So really, for us, this has been a revolution.
So what is the groundbreaking science that we are doing with this data set, Taimur?
Very good question. So I think it's very clear now that we can learn a lot about these two massive ellipticals by looking at these faint features around them, by looking at the global clusters. But these are not the only objects in this image. We can see galaxies all over the frame. For example, if you look at the top of the frame, you can see this very beautiful edge-on disk galaxy, and on top of it, there's a faint galaxy, objects that we call dwarf galaxies, and they're actually all over the place. We can detect about some tens of these dwarf galaxies in this image. Also, Francesca showed that there have been some new discoveries around NGC 6744, so they're everywhere. So we need to find them more and more. We need to study how the numbers are, how the distributions are. They can tell us about dark matter. They can tell us about formation of star clusters within them, and a lot more that we hope with Euclid we can discover about.
Thank you so much, Taimur and Karina, for being here with us today at ESA.
You're welcome.
And now we are going to unveil the image of a galaxy cluster Abell 2764. And for that, we have online connection with Dr. Hakim Hatek from the Astrophysics Institute in Paris. Hello, Hakim.
Hello, Sandra.
We will display this spectacular image for everybody to see and come back to you in a few seconds.
All right.
We are seeing a very beautiful image of the universe here. Can you describe it for us?
Indeed, in this beautiful picture of Euclid, we see many interesting things. In particular, we see a massive galaxy cluster here at the top right corner of the image. So this cluster contains dozens of massive galaxies orbiting a dark matter halo. And apart from this galaxy cluster, we see an impressive number density of sources in this image. This is what we call a blank field, because it's more representative of the large-scale distribution of galaxies in the universe. And this was possible thanks to the wide field of view of Euclid. And to give you an idea, this patch of the sky corresponds to only one pointing of Euclid, and the mission will map 30,000 times this area, which is essentially 1/3 of the entire sky.
Indeed, we see a large amount of objects here. What are we looking at?
Yes, so we were able to identify 250,000 objects in this single image. So it contains many distant galaxies, many distant galaxy clusters like Abell 2764, and we also see a very special type of galaxies, which are the most massive galaxies known in the universe, in the center of these galaxy clusters. And we also see in this Abell 2764 cluster an age-old galaxy, and thanks to the sharp view of Euclid, we can even measure the thickness of the disk in this galaxy.
And what can we study with all this data?
So from this picture, we can actually identify some of the rarest objects in the universe thanks to the wide field of view of Euclid. So we identify some of the brightest and most massive galaxies in the early universe. Thanks to that, we can also study how these objects, along with supermassive black hole, helped shape the entire universe at early times. And we can also further study the intracluster light, which is the light emitted by stars that are ripped away from galaxies into the intergalactic medium. And we know that this light can trace dark matter, so it can help us also map the 3D distribution of dark matter in the universe.
We are seeing a very bright object in the lower part of this image. But this is not a galaxy, right, Hakim?
It's not. This bright object actually is a star that lies within our own Milky Way, our own galaxy. In general, when you look with a telescope at a star or at point source, the light is scattered away in this spiked shape typical of the optics of this instrument or telescope. And Euclid was designed to make this scatter as small as possible. As a result, we can measure in great details accurately the shape of galaxies, but also detect distant galaxies without being blinded by these bright stars. And this is precisely what defines Euclid's sharp view of the universe.
Thank you, Hakim, for this amazing explanation.
Thank you, Sandra.
Let's now discover our last picture, Abell 2390. If you remember earlier in our program, we mentioned dark matter, and now with this neat footage, we actually can go deeper into this subject. For that, we are connected online with Jason Rhodes from NASA Jet Propulsion Laboratory in California. Hello, Jason.
Hello, Sandra. I'm really excited to be here to talk about this Euclid image.
We're going to look at this picture, and we will go back to you very shortly. So Jason, can you explain us what are we looking in this amazing view of the universe?
Yes, this is another huge image taken by Euclid. This image is of a galaxy cluster called Abell 2390. The exciting thing about this image is a number of cluster galaxies in the center of the image that are associated with each other and gravitationally bound. But Euclid is able to take a picture not just of this cluster of galaxies, but the entire surroundings of the cluster of galaxies. And in this picture, we see this cluster of galaxies that's about 2.7 billion light years away. That means it took 2.7 billion years for the light from that galaxy cluster to reach us. And Euclid is able to take images not just in the visible light like we see with our eyes, but also at the same time take images in infrared light, heat vision. And this allows us not just to measure the shapes and positions of the galaxies, but also the distances to these galaxies.
We normally cannot observe as many galaxies as on this view, right?
What's impressive about Euclid is its very wide field of view. Most telescopes would allow us just to look at the center of this galaxy cluster and see the galaxies in the cluster itself. But Euclid's wide field of view allows it to take a very large picture that gets not just the galaxy cluster, but the outskirts of the galaxy cluster and the galaxies surrounding the galaxy cluster. One really exciting aspect of this galaxy cluster is it contains a lot of galaxies, and so it has a lot of stars and a lot of mass in the form of dark matter. And in fact, this galaxy cluster has about the mass of about 10 trillion suns.
We have previously talked about dark matter. How is this image related to it?
So Euclid's wide field of view and ability to take images simultaneously in visible and infrared light is a really unique capability that's going to allow us to take images like this one that allows us to measure the shapes and distances to many, many galaxies. And that's going to be a great benefit as we try to understand the properties of dark matter.
But Jason, if we cannot see it, how we know dark matter is there?
So dark matter is invisible. It doesn't give off light or absorb light. So we can't detect it directly, and we have to detect it indirectly. One of the techniques we use to detect dark matter is by looking at distant galaxies. And the light from those galaxies comes to us, but its path is bent when the light goes near a conglomeration of dark matter. This is a consequence of Einstein's theory of relativity, which tells us that gravity bends space. This technique of gravitational lensing of distant galaxies is what Euclid is designed to measure. Typically, we see very small distortions in the shape of these distant galaxies, but in the case of Abell 2390, there's so much dark matter in this cluster that the dark matter severely bends the light from some of these background galaxies. And one of the things we see is these giant arcs here, these smooth arcs that are curved. Those are actually very distant galaxies that have their shapes hugely distorted by the gravity of the dark matter in the cluster. And some of these arcs are even multiple images of the same very distant galaxy. Over the course of its 6-year survey, Euclid will survey many thousands of galaxy clusters across a third of the sky, allowing us to take detailed observations of the dark matter in those galaxy clusters, and thus learn about the distribution and amount of dark matter in the universe.
We have detected a lot of dark matter in these galaxy clusters. What can we learn about the nature of the universe?
By looking at the dark matter in these galaxy clusters, we can learn about the distribution and amount of dark matter in the universe. And looking at how that evolution of that dark matter distribution goes over time, we can learn about the effects of dark energy on the universe. And this is what Euclid is designed to study. Additionally, galaxy clusters give us another great laboratory to study dark energy, because the number and mass and distribution of galaxy clusters in the universe is a great measure of the interaction between dark energy, which wants to push things apart, and gravity, which wants to pull things together.
Thank you so much, Jason, for connecting to this special program on Euclid. And now that the Euclid mission has entered its main science phase, we are looking forward for more groundbreaking discoveries. We can expect the next public data release around March 2025. Stay tuned for more incredible science. I would like to thank the ESA Web TV production team, Professor Mondell, and all the Euclid scientists who joined the program today. But most of all, thank you for your continued support on this historic mission. Go Euclid!